Hey, it's Mr. Shrum, and I'm going to go through the electromagnetic radiation tutorial and some of the lesson activities. And we have to do some calculations in this one. But electromagnetic radiation is the fancy word for light. Life is dependent on sunlight directly and indirectly. Plants require sunlight to photosynthesize their food and survive. Animals, including us, depend on plants for foods. And as humans, we're one more link up the food chain, deriving our food from plants and in some cases, animals. We know that energy exists in various forms, and one of these forms is called radiant energy. That's the energy of electromagnetic waves, which travels through space in the form of electromagnetic radiation. Visible light, X-rays, radio waves, and microwaves used in a microwave oven are all examples of electromagnetic radiation. Here is the spectrum, the electromagnetic spectrum. And in the quantum model of the atom, an electron in a higher electron level has more energy than one in a lower level. These electrons can jump up to energy levels. And every time an electron jumps down, a photon is emitted. When an electron drops from a high energy level to a lower energy level, it emits this packet of light energy, and we call this a photon. An interesting application of this is a laser. Photons are emitted with the electrons when the electrons give off the extra energy and then return to their usual lower orbits. So energy is put in to excite the electrons into higher energy orbits. And then once they come back down, they emit those photons. And we can see those photons being used in lasers. Neon signs use these, and fluorescent lights use the same principle too. Light behaves like a wave and a particle sometimes. But here we're going to look at waves. Both of these waves start at the rest line from point 0 or point O, and they reach the highest point P. Okay, pass the rest line again, reach the lowest point, and then come back to rest again. That is one cycle of a wave. And then that wave cycle repeats over and over again. We call the highest point of a wave the crest. So points P and R are crests. The height of P from the rest of the line of the wave is called its amplitude. Notice these guys have different amplitudes. One's higher than the other. And the distance between two consecutive crests, that is the distance between point P and R, is called the wavelength. And we represent the wavelength with a Greek letter, lambda. And the number of cycles that pass through one point within a certain amount of time is called the frequency of the wave. Here is the spectrum of the electromagnetic spectrum. And here is the visible spectrum to us, okay? This is visible light. These other ones exist, and we just can't see them, right? There are radio waves traveling through the air, X-rays too, but you just can't see them with our human eyes. All waves in the electromagnetic spectrum in a vacuum travel at the speed of light, which is 3 times 10 to the 8 meters per second. here are the electromagnetic spectrums and the region, their frequencies, and the wavelengths. X-rays, gamma rays are the smallest and very, their frequency is very high as well. The longest waves are radio waves, and their frequency is low, their wavelengths are long. So wait, just kidding. Oh man, I screwed up. So radio waves are the longest. That was weird. Okay. Classical electromagnetic waves. Classical electromagnetic waves, radio waves have the longest wavelength, like we said, invisible to us, undetectable to us, but it totally changed the way we live. And with the exception of light, you probably come across radio waves more than any other wave from the electromagnetic spectrum. So our TV signals are carried by radio waves, the waves in our cell phone, and of course the radio as well. Radio waves can transmit conversations, music, and pictures over millions of miles. And this is how, essentially. When an electric current passes through a length of a conductor, such as a radio transmitter, the electrons in the conductor gain energy and begin to oscillate. Oscillate means to move back and forth like a wave. The oscillating electrons produce both an electric field and a magnetic field. So this is electromagnetic radiation. There's electric energy, right? And magnetic energy. When the oscillating electrons move, the direction of these fields and the force they exert change at the same time. And here's a lesson activity. We're going to launch this activity. There we go. Okay. So this shows a radio station with a transmitter and a receiving antenna. The transmitter generates radio waves. The receiving antenna picks them up. Your task is to follow the instructions and answer the questions below. Part A. Click oscillate in the right panel and observe the radio transmitter. Okay, so There it is, oscillating, doing its thing. It's moving up and down. You see the wave? Okay. The moving electron in the transmitter generates a radio wave, which moves towards the receiver. Click electric field. What do you notice about the wave generated by the moving electron? Here we go. Well, we have the direction of the wave generated by the moving electron is opposite to the direction of the force it exerts. So here's the electric field. Sorry, here we go. So the direction of the wave is moving this way. It's moving to the right. And yet the force, the electric field, is opposite of that to the decrease the frequency of the electron on the transmitter by using the frequency slider. What relation do you observe between the oscillating electron and the frequency? So here's frequency, and we're going to reduce it. So it slows it down. As the frequency of the oscillating electron decreases, the frequency of the wave decreases. As the frequency of the oscillating electron increases, it also increases the frequency of the wave. Okay, excellent. Change the frequency of the electron in the transmitter and then watch the changed radio signal traveling to the receiver. What do you notice? It takes time for changed radio signal to reach the receiving antenna. Once it does, the electron oscillates with a new frequency. When you increase the oscillation frequency of the electron in the transmitter, what happens to the wavelength of the wave? When you increase the oscillation frequency of the electron in the transmitter, the wavelength of the wave decreases. So here we go. It gets faster. Okay. And then if we reduce it, the wavelength gets longer. Okay. True. True. Check electron positions. Observe the time graph of the transmitter and note the number of bars between any two peaks of the wave. Now increase the amplitude of the electron by dragging the amplitude slider. Wait for 2 to 3 seconds. And again, note the number of bars between any two peaks of the wave. What do you observe? Okay, electron position. Wait. I don't know what does that mean. Check electron positions checkbox. Is there the time graph? I don't see anything. So if you increase the amplitude, that happens. You can see the transmitter receiver stuff here. And you can count the bars in between. Let's. Oh, whoops. So that did not change the wavelength of the wave. Okay. All right. According to quantum mechanics, electrons oscillating in an atom do not give off waves continually. They must change energy levels to emit light. Nevertheless, classical electromagnetic waves, like radio waves, do share some common characteristics with light. The frequency of the emitted light is directly proportional to the energy given off by the electrons. The higher the energy given off by the electron transition, the higher the frequency of the emitted light. This energy is expressed by the equation E equals hv. H represents Planck's constant, which is 6.626 times 10 to the negative 34 joule seconds. This equation is known as Planck's law. The frequency used in this equation is mathematically related to the wavelength of the radiation. The relationship between frequency and wavelength is the same for all types of electromagnetic radiation, from high energy gamma rays to long wavelength radio waves. It's the same relationship no matter how the radiation is generated. Frequency and wavelength. All right, so there is a relationship here that we can use to establish a mathematical relationship between in the form of an equation. In the radio wave simulation, you observed that when the frequency of the radio wave increased, its wavelength decreased. So as frequency goes up, wavelength goes down. Since this pattern is the same for all electromagnetic waves, we can conclude that the wavelength and frequency of a wave are inversely proportional to each other. As frequency increases, wavelength decreases, and as frequency decreases, wavelength increases. When the frequency and wavelength of an electromagnetic wave are multiplied, the product is equal to the speed of light, which is constant in a vacuum. We can just express this C equals wavelength times frequency. Okay. And C denotes the speed of light, which is almost 3 times 10 to the 8 meters per second. Lambda is the wavelength, and nu, which is the fancy Greek letter for that, and it's a stand-in for frequency. From this equation, we can derive the following equations to calculate the wavelength and frequency of a wave. And here is an example of calculating the wavelength and frequency using this equation and the speed of light. And that's that. And be careful with the powers of the tens. That can confuse some people. And this is it. So here we go. With the value of the speed of light being 3 times 10 to the 8th, use this equation to match the frequency of each wave to its correct wavelength range. Drag the items on the left to the correct location on the right. Okay, so we're gonna do, you would put this in your calculator, right? And I am just gonna use the information that we already know. Gamma rays, smallest wavelength, microwaves, larger wavelength. Smaller the wavelength, larger the frequency. Larger the wavelength, smaller the frequency. Okay. So we want to have highest frequency be gamma rays. And then we have microwaves being the smallest frequency. And then visible light. Try it. And then just flip these. That makes sense. Visible light is a smaller infrared. Yay. Cool. Okay. But another way you could do that is just to plug those into the calculator. And that's it for electromagnetic radiation. Visible light, which is necessary for our survival, is in fact only a small subset of the radiant energy that travels through space as electromagnetic waves. It's made up of waves that are characterized by their amplitudes, wavelengths, and frequencies. Long wavelengths, such as the electromagnetic waves like radio waves, are produced by oscillating electrons. The frequency of the wave is directly proportional to the oscillation frequency of the electron. On the atomic scale, radiation is also emitted by changes in quantum energy states. When electrons change energy states, moving from high energy to low energy, it emits a photon. And we also came up with this equation. We showed how the energy is related to frequency and wavelength as well. And that's it. Okay. So remember these equations. You'll be able to use them on the tests. And that's it. If you have more questions about this, let me know and I can explain these concepts even further. But until next time, have a good one, and I will see you all next time. Bye-bye.